Okay, so this will probably be a short one, but so I want to talk about rational functions. A rational function is just a function that's a polynomial divided by another polynomial. Um, so since we're talking about division, I'm going to state a theorem. This is a theorem that's very similar to things that we've proven. I'm not going to prove this one. It's so this is just if the limit of x goes to a of f of x is L, and the limit as x goes to a of g of x is m, and m is not 0, then when I do the limit as x goes to a of f of x over g of x, I get, well, it's the limit of f of x is L, the limit of g of x is m, so I get L over m. This is why it's important that m is not 0, otherwise we would be dividing by 0. L can be 0, that's fine. I can have 0 on the top of a fraction, just not on the bottom. So just for a really simple example of this, let's do the limit as x goes to 1 of x plus 1 over 2x plus 1. I've got a polynomial divided by another polynomial. I have this theorem, so I'm allowed to do the limit of the top divided by the limit of the bottom. And actually, let me break this down. Because I just want to show that I'm using the above theorem to do the limit separately on the top and the bottom. And this will work as long as I don't get 0 on the bottom. And maybe showing this amount of work is excessive, but I know the top is a polynomial, so I get this limit just by plugging in 1. And I know the bottom is a polynomial, so I also get it by just plugging in 1, and I got 2/3 the same way I said I would. Okay, but that's easy. Let's talk about the next one. And on the next one, I can try to do the same thing. Oh, hope I don't have coronavirus. I can try to do the same thing, but I'm going to get 0 on the top and on the bottom. Of course, the bottom is the real problem here. But if you remember Calc 1, you probably basically know what we're going to do. I'm going to factor so I get this, and now I want to say something technical, and of course we all know what's going to happen. I'm just going to cross these off and I'm just going to get x plus 1. But let me say something technical about why I'm allowed to do that. This is equal to this as long as x isn't 1. Right? If x was 1, this side would be undefined and this side would be 2. But as long as x isn't 1, I can cancel this and I get x plus 1. So why am I being so technical about this? It's just because this doesn't always equal this. It's possible that this side is undefined and this side is defined. But say if we have two functions and they're always equal except for maybe one certain value of x, then they have the same limit as x goes to a. So why is that? It's because, so let me find the definition of limit here, just so I can show it to you. Yeah, so this is just from the first day of limits. So there's the definition. And so it's because of this. In the definition of limit, we only care about values of x that are different from a. Right? Because, and this is why this greater than 0 actually matters. We've been ignoring that usually. Usually the important part is just that this is less than delta. But it's also important that this is greater than 0 sometimes. Because if x was equal to a, this would be 0. Meaning that we only consider values of x that are different from a. When we're calculating a limit as x goes to a, what happens when x equals a does not matter at all. In other words, if these two functions are the same for all x not equal to a, then we don't care what happens when x does equal a. As far as we're concerned, for a limit, these two are the same function. The fact that they disagree when we plug in this one number does not matter. So, essentially, I can treat this as being equal to this. So maybe let me put some lines around this note, and then I can pick up from here. Because this is the same as x plus 1, as long as x is not equal to 1, and I'm doing a limit as x goes to 1, I can replace this with this. And now this is just a polynomial, so I can just plug in 1 and I get 2. Oops. Sorry. Yeah. Let me do another example like that. Maybe this is easy for you, but I'll do this one faster because we already got through that note. So once again, I see a rational function. My first attempt is to just plug in x. If I plug in 2, let's check the bottom first. I get 4 minus 2 minus 2. I do get 0 on the bottom. So let's hope we can do something like that again. The bottom is, I'm just going to guess, one of the factors is x minus 2, because that's how you would get a 0 on the bottom. And then the other factor should be x plus 1. Now, on the top, what I would really like is I would like to be able to cancel this x minus 2. So I'm hoping that I can factor the top into x minus 2 times, yeah, it looks like x minus 2 times x plus 5. There we go. And now, based on what we've discussed, I am justified just crossing these off, because as long as x is not 2, then these are both defined and I can cross them off. And now I'm doing a rational function, so I just plug in x. Oops, I don't need this anymore. I'm just plugging it in. 7/3. Yeah. Okay,